Hello and welcome to our channel again. So here I am Suraj with a new video of mine where I'm going to discuss about a question related to the quantum mechanics. So we have discussed various types of the things in the quantum mechanics, and now we are in a stage to solve the different types of the problems related to the quantum mechanics. So this is our first problem in the quantum mechanics, which is related to the normalization. So if you have not watched my videos on the normalization, you can watch my video so that you can understand that what this particular question is saying. So now let's start to doing this particular question. So now let's start our solution of this particular quantum mechanical problem. So the main concept that is used in this particular question is the normalization. So let's apply the normalization formula. So what it says is that integration from the negative infinity to the positive infinity of our wave function xt mod square, and here it can be written as dx can be written is equals to the 1. So this is an obvious explanation, and why it is equals to the 1, you can watch my previous video where I was explained about this particular thing, that why it is equals to the 1. Okay, so now next what we can do is that you can think that our wave functions contains the imaginary part. Here you can say that it is iota. It means there is an imaginary part, and now we have to do some different configurations. Okay, so what our thing is that integration from the, I will do not put the sign of the integration and just become messy. Okay, I am not doing to write here, but yeah, you have to remember that here the limits are from the negative to the positive of the infinity. So let's write our particular expression. So what we can write is that if there is a complex part in our wave function, we can write our this particular thing as the size. So when there is some sort of imaginary part in our wave function, we can write our normalization thing like this: psi star xt, and here normal psi xt dx is equals to the 1. Okay, so this is what I think we can write. So what is that psi star? Psi stars means the complex conjugate of psi, because now you can see in this particular expression that there is an imaginary part, not in real. There is an imaginary part. This is not contained real parts. Yes, it contained real parts, but it is a mixture of the real and imaginary. So it is imaginary parts. So how we can write our normalization thing like this? Okay, so now evaluating our integrals. How we can evaluate it? Just by putting our values, and let's get it. Integration of, what is the value of psi here? So psi is equals to, okay, a e to the power negative a m x square m x square divided by the h cut. Okay, so how we can write our imaginary parts? If I study the complex number, the complex conjugate of empty number can be written as negative iota. It means you can see here that this is our positive iota. So that if I take here the complex conjugate of this particular expression, this expression can be written as negative. Okay, so what I have written here, and again multiplying it by our a e a mx square divided by the h cut, h bar, whatever you say, and plus here iota t here, and dx is equals to the 1. Okay, so this is our expression, what it look like. So let's simplify this our equation. Okay, now integration of a e negative a m x square divided by the h cut, and into a e minus minus plus a iota t. So as you can see here that using the laws of exponents, I just separate out it, because if you take the, if you reapply the formula of the exponent, you will just get this particular expression. Okay, and into breaking this as a e a mx square divided by the h cut. Okay, here, and here a e to the power Oh, sorry, here is minus sign. Okay, so here is minus sign, I think. Yeah, there is minus sign here. Okay, so here is a minus sign, and then it's become minus. Sorry, okay, then we can say that here it's become, here is expression contains minus. Here it contains a e minus a iota t dx is equals to the 1. Okay, so we have simplified our expression. Now we cut out this equation, will get cut out. How we can see that? So as you can see here, that integration here a e minus mx square h cut, and here these. Okay, so let's see this and this. How we can write these two? So we can write it as a e minus 2a mx squared divided by the h cut. Yes, we can write it. And how this expression can be write? We can write this expression as a e ait and minus ait, and which will become e to the power 0, and e to the power 0 will become, okay, let's simplify this in the next expression, next step. Okay, so what we can now write it as integration of a e minus 2a m x squared divided by the h cut into a e to the power 0, because if you take this and this will cut out and this will become 0, a to the power 0 dx is equals to the 1. So this is our what equation become, and if you do e to the power 0 is equals to the 1, and this our expression can be written as this. It can be written as integration of a square e to the power negative 2a mx squared divided by h cut dx is equals to the 1. Okay, so this is our expression, and simplifying our equation we write it as this. Now we are going to do some of the integration by substitution. Okay, so yes, we can evaluate this particular integral by the substitution method. So let's see what will happen. So let's choose me another color. Okay, so here integration by parts we can choose. If you have know the integration by parts, then it's okay, you can find out. So it's very easy. So let's take e minus e to the power minus 2 am x squared divided by h cut st. Okay, so this is a rough work I am doing here. Okay, this is our rough work. So how we can do this? So do the differentiation on the both side with respect to the x. What you will find is that by say the chain rule, we are applying here the chain rule, and what we get is that minus to the power 4 a m x square. Okay, and this is particularly equals to the, okay, okay, so here this expression cannot be used by the integration of substitution, I see, because then it will become x. Okay, so this is the one of the example of the Gaussian integral, and I am applying here the integration by parts. Sorry, this is the not can be done by the integration by parts because the x factor will here again remain. So I think we can do this particular by the Gaussian integrals. So in my next video I will provide you a good format of the Gaussian integrals, that what is Gaussian integrals, not the proof, because proof of the Gaussian integrals are very complex. So now I'm going to write out and figure out that which type of the Gaussian integral we can use here to solve our particular expression. Okay, so let's see that which Gaussian integral we can use. There are 3 to 4, I think, remember, there are Gaussian integrals, and which will apply. Let's see here. So sorry, we can't apply here the integration by substitution. If there is only x, then we can apply the integration by substitution, but no, this cannot be done by the integration by substitution, as is a complex thing, and I do not remember the formula of the Gaussian integrals. So I will check out what's the formula of the Gaussian integrals. Okay, here, as you can say, I have written the formula of one of the Gaussian integral, and we are going to evaluate this integral, which is the integration of e to the power negative x squared divided by a square dx is equals to the a root pi. Okay, so first of all we have to change our this particular integral in this form. So how we can do this? So let's see here. A square is a constant, take it out from the integration sign, and integration of e to the power negative x square divided by the a square. Okay, so what I have done here and how I write here in this form. So let's see here. So you can see here that if we change our this, so I'm going to write here that how I have written it as e to the power negative x square. Negative x square is already written there. So what we can do is that we can divide a root under h cut. Here we can see we can write it as a root under h cut divided by the 2a m. So can we write it like this? And doing here the square sign. So is this not similar to this particular expression? Because if you square it, it removes its square root sign and it will just becomes x square, and 2am will just put on side of the numerator side, and it will become negative of 2am x square divided by the h cut. It means from this what we have substituted our value of particular a. So our value of a here is what equals to the root under h cut divided by the 2am. Root under h cut divided by the 2am. So this is our particular expression of a. Okay, so this is our particular expression of a, and now we are going to evaluate this integral because now it's become very easy to do this. And here dx is what equals to the 1. Okay, so next evaluating it, what the value of this particular integral? The value of this particular integral is nothing but it is a square root on a square, capital A square. Okay, so this is a normalization a, and this is a small a root under pi. Root under pi is equals to the 1. Root under pi, and it is equals to the 1. So this is our particular expression. And remember, the whole in this particular explanation, the integration sign and the limit is from the negative to the positive infinity. Now how can we write our this particular a square? So we can write it as a square. And what's the value of a here? So value of a is nothing but h cut divided by 2am. So this collectively become nothing but the h cut. So I'm going to write here that what is becomes collectively when I write it, it will become divide, it will become root under h cut pi divided by the 2am is equals to the 1. Okay, so this is what equation become. And now putting on another side, what we will get is that a square is equals to the root under 2am divided by the h cut pi, and putting another the value of a will become nothing but 2am divided by the h cut pi 1 by 4. So this is our value of the normalization constant a. So this is our whole explanation on solving our this particular question, in which we have to find out this particular quantity, this particular a quantity. And the wave function is also here, you can see here, contains the imaginary part. Okay, so evaluating all these things, we are left here with our value of the a, which is 2am, 4 pi, and 1 by 4. So as you can see here that this is a typical mathematical question mainly, not mainly a quantum mechanical question, because it deals with the mathematics. All the thing is mathematics, and if you do the mathematics, then you can get the answer very, very clearly, easily. Okay, so this is our video on this particular explanation of the how to calculate the normalization constant a for any of the given wave functions that is here. For in this case, however, the wave functions normalization constant a is what equals to this particular quantity. So there may be some another a for different wave functions. So this is my video where I will where I explain about how to calculate the normalization constant by using a simple analogy of the normalization, which is negative to the positive infinity of the psi modulus x squared tx is equals to the 1. So thank you for watching my video on this particular topic, and I will also make a video series on the different types of doing questions in the quantum mechanics. So one of the question is this question, which is a sort of an easy question. And in next video, we're going to discuss about very hard question related to the quantum mechanics, which deal with mathematics also, and also the quantum mechanical problems. It means we have to think. In this question, I will say this is a mainly mathematical question, but when you deal with the potential questions, these questions are really very good, and we are going to discuss in the next video. Okay, so thank you for watching my video.